So for the session now, I'm going to give a very broad overview of our introduction into synthetic aperture radar, because we're hearing a lot more about the processing of it later today, and also having a hands-on session on change detection with this data set. So the most important thing about the synthetic aperture radar is that it's an active sensor in contrast to a passive sensor. So the passive sensors are like all of the optical satellites. They acquire the light that is reflected from the Earth, which is coming from the sun. And so you have the sun as the source, and then you just have a receiver at the satellite. In an active system, you have a source of microwave in the case of Sentinel-1, and then you acquire what's coming back. Other active remote sensing techniques are LiDAR data, for example. And then, so this is what this looks in for real data. So this is on the left, Sentinel-2 image of the Terceira Island, and on the right, the Sentinel-1 image at roughly the same dates. On the optical data, you see you can clearly distinguish the sea. Then you can also see the agricultural areas. You see we have a mouse here. No, it's not working. So you see forest areas here, and you also see some of the urban structures. In the SAR image, it's a bit getting used to looking at that. So you also see the open water as clear black areas, but in the ocean, you also have roughness effects on the waves. And then you can see the urban structures in white. You can clearly see the airport because it's a very smooth surface. And I'm going to go into more detail why we see what we're seeing here. But you can't as easily see the differences between the agricultural and the forested areas. So why do we even bother to look at this data? There are clouds, and this is just the average cloud cover of November last year. And so every area that is purely white is just fully clouded for months. And so you have a lot of areas where you can't acquire any data, or you also can't, or you only have some data at some parts of the year. And with SAR data, you can acquire data on a regular basis, because it's able to go through the clouds, because it's using microwave data instead of the optical wavelengths. And also it's able to acquire data on the Arctic, for example, during wintertime, which is not possible in optical data. So SAR data has been used since the 1970s. So the first actual SAR satellite was the CSAT mission by NASA in 1978. Then there have been 3 space shuttle missions, of which the SIR-C mission acquired the data for the SRTM global elevation model. And then in the 1990s, the ESA started to launch the EIS-1 and 2 satellites. Then the Canadians started to launch RadarSats. Germany started the Tandem X missions in the beginning of 2000s. Japan has a long tradition of using L-band data, and then with the launch of Sentinel-1, I think we reached a new era of SAR data, because now we have a continuous acquirement, so a continuous acquisition of C-band data on a regular basis. So they try to cover the whole Earth and some parts of the Earth on a much more regular basis, but at least every part of the world once or twice a year. And so, and then also they're starting to get private companies like ICEYE that started also a few years ago, and there are new satellites planned, like the Biomass mission, the NISA mission, or ROSE-L. So the Sentinel-1 data is like, this is the global coverage map of Sentinel-1 data that is available. So you can clearly see it's a European focus because it's European funded, but also you have a lot of acquisitions on different parts of Africa, different parts of Asia, also the whole Greenland and parts of the Antarctic. Yeah, it's basic. I mean, the maximum number of images is 1,600 images in the last 7 years, and so it's nice that it's just going to be repeatedly acquired. So to talk a bit about the acquisition mechanism of SAR, so it's a side-looking radar, so it's not looking down like an optical satellite, but it's looking in an angle of 25 to 45 degree, and you have differences in the near range and the far range, but I'm not going to go into detail here because I think this will be covered in the afternoon by the SAR processing plenary. But with this side-looking acquisition mode, you get some geometric distortions that you need to be aware of. So if you have a high mountain, you could have shadows in the image because you can't reach what is behind the mountain. You can have foreshortening. This just means that the slope of the mountain that is turning back away from the satellite is appearing larger in the SAR geometry. So it's like these two slopes have the same length in the actual geometry on Earth, but in SAR one is shorter than the other, and therefore on this pixel there's much more. This would be much brighter because it's getting more energy from the same area on Earth. And then you can have an extreme case of this foreshortening where you acquire the tip of the mountain before you acquire the bottom, and then basically your mountains look like they are flipped a bit. And so these are examples. So I would like you to shortly think about what could be what in these effects. And so the foreshortening is these brighter appearing areas here, which are just that's just a bit brighter. Then the shadows are easily distinguished as very dark areas where it shouldn't be that dark because there's no water or no other reflectance. And then you have the layover, which is just these smoothing of the mountain areas. And so with this SAR, you have also different, you can have different scattering principles. So the first one is just rough surface reflectance on some open area. So that would be A. So you send the microwave is sent on the surface. Then you have some scattering process, and most of the energy is just randomly distracted somewhere, and then parts of it is coming back. Then in B you have a double bounce between the surface and some natural structures. So this could happen, for example, at the edge of deforested areas, or generally at the edge of the forest, where you have a bit more backscatter because you first hit the smooth-looking trunk of the tree, and then you hit the ground, and then you get a bit more back than in the rough surface. This would be much more pronounced in urban areas. That's why these urban areas are showing up as very bright areas, because you have man-made structures which are very smooth, and then you also have smooth concrete on the ground, and therefore you have this double bounce effect where a lot of energy is reflected back to the SAR signal to the satellite. And you can basically have the same if you would have standing water beneath the canopy or at the edge of the canopy. And then you also have the so-called you can have the so-called volume scattering. So you can, depending on the wavelengths that you're working with, either have a scattering mechanism directly on top of the canopy, like in D, or you can have interactions between the microwave and the canopy cover inside of the canopy, and then you can have a bit. You also get random reflections, but you get a higher backscatter value than on the rough surfaces. Then another distortion that you should be aware of is that these images are looking a bit noisy, because they are this is the so-called speckle effect, and this is because you have a coherent system that is sending the microwaves in all the same phase, and then you have random interactions. So this is how this looks if you zoom in. So it's in one agricultural field where the surface is actually the same, but you can have random effects from the phase, which would then induce this. And so the reason is that you send down your signal, and then the signal interacts with the scatterers, and then because you have a much larger area than your wavelengths. So the wavelength is in a range of a few centimeters to maximally a meter, and then you have multiple scatterers that are going back, that are sending the signal back to your satellite, and then because it's a complex signal, so you have a phase, and then so you have an real and an imaginary part, and then you basically sum all of these different scattering processes together to get your final result, or to get your final and then you can compute the amplitude from that. But because these phases can be different depending on whether some scattering process is happening here or here, you get these random shifts, and then the sums can be either very high or very low, and therefore you have these random looking differences between pixels on the same land surface. And then to deal with that, you could use a speckle filter. So I'm not going to go into much detail, but we also did a study on that to because normally you can either do so-called multi-looking by averaging in different neighboring pixels, so you're smoothing the image, thereby reducing your spatial resolution. And then there are ways to just to mix this and to have a spatial average and a temporal average. And we did a study on only using the temporal information, because with Sentinel-1 we have a very high repetition rate. So we have an image every 12 days, and then we can use this temporal information to also smooth the data. And we showed that we get a similar smoothing to other techniques, but without losing spatial information. So might be interesting, or so it depends on the use case whether it could be useful to use. And then another thing to know about is the so-called polarization. So you can have the wave either going vertically, so either moving up and down, or it's moving horizontally. And this influences how the SAR signal interacts with the lens surface. And basically the satellites that are in orbit can either send the data vertically or horizontally, and then some of them can then acquire the backscatter also in vertical or horizontal. And Sentinel-1 can only acquire, so Sentinel-1 can send both polarization types, but it can only send one at the same time, and then acquires the same, and then acquires the vertical and horizontal together. So therefore it's a so-called dual polarized satellite. And then, but there's also quad pole systems that can send both polarizations at the same time, and then receive both, and then derive more information from that. It's just to give a short idea of what might be the differences between the polarization. So on the left, it's the VV data again, and on the right, it's the VH. So it's both vertically sent and then received vertically or received horizontally. And you can see that the VV image is brighter in general. You have you see more of the man-made structures like this, or also here in Anga do Heroísmo. And but then on the other on the VH, you see a bit more the differences between the agricultural areas here, and you can see certain patches of different agricultural fields, and then you also see patches of forest areas. And then you can also combine these in making a RGB image of the VV, the VH, and the ratio data to derive even more structure from it. And so you see some mountain range here. You see the volcano, and also here you see more differences between the different fields or different agricultures. And another thing that changes the acquisition of the or that changes how your image looks is the wavelength, as I said. So it's from a few centimeters. So the X band, like in tandem X, is 3 centimeters. The C band in Sentinel-1 is like 6 centimeters, and the L band is 20 to 20 to 30, depends a bit on the satellite. And then you have the P band, which is now going to be sent into space in the ESA biomass mission, which is at 70 centimeters. And so the rough idea to work with these different wavelengths is that you can imagine that the microwave is interacting with everything that is at least as long as the wavelength. So with X band, you have an interaction only with things that are shorter than, or you can penetrate only through things that are shorter than 3 centimeters. So therefore, that's why in a forest you would interact directly with the canopy cover or with the top of canopy. With C band, you interact with everything that is 6 centimeters. Then you have you can go through a bit of the forest. You can go through some of the other vegetation types like grasslands and wheat and so on. With L band, you can go basically, the signal goes through the whole forest canopy and then interacts with most of the stem structure and some of the branches. And in P band, you only see, or the satellite sees only the overall trunks and stems and larger things that are there, and it's not interacting with all of the leaves and all of the small branches. So I just wanted to also shortly mention a few use cases that SAR data is used. So there's a lot of interaction with soil moisture because the SAR signal not only depends on the geometry, but it also depends on the dielectric properties. So in natural areas, that basically means, is there water or is there no water? And human structures, this could also mean, is there a metal plate somewhere, because the microwave is just going to interact with the metal or with other man-made structures like windmills or power lines. And then you have a surface water dynamics use cases, because on top of undisturbed water, you have a clear reflectance going back from the sensor, and thereby the open water areas are appearing as clear black areas in your image. Then you also have a large community using that for sea ice and also for glacier monitoring, but I'm not really I don't have any deeper knowledge about that. Then it's also used for above ground biomass detection. It's used for ship detection. The phase information can also be used for ground motion and just small changes in the small movements in the ground. And we can also use it for change detection. And just to give some real life examples that I found online are, for example, flood mapping based on for the typhoon in Africa a few years ago. So the flooded area is basically shown in red, and this information is derived of multiple Sentinel-1 images. And then there's also maps of above ground biomass derived from L-band data, and also a lot of work on doing ship detection and using this to track ships in the open ocean. Yeah, and that's the end of my presentation, and I'm open for questions. Yes. I was wondering what the pattern of sampling that was shown in the global map was very linear. And I'm sort of assuming that because there's an energy source that's needed, so they only figure out satellite, or maybe because we transmit the data, like an on switch. You mean this? Yeah. Yeah. So there's basically two things hindering more coverage. One is you need energy for the SAR data, right? You need a lot more energy than in an optical satellite, because you need to send the signal from the satellite. But I think, I'm not entirely sure, but I think even more importantly is the downlink. You need to then get the data down to Earth. And you saw that this was a huge problem because a few years ago, I think in 2018, ESA launched the data relay satellite. So basically, you have so you have your Sentinel-1 going here, and then you need to fly over a ground station to get it downlinked to Earth. And instead of that, you have another satellite that is somewhere else, that is then seen from Sentinel-1, which downlinks that to some of the ground stations. And that, I mean, I'm not sure what currently are the main restrictions, but at least from looking at the time series data of Sentinel-1 that I worked with, you saw a clear increase of available data somewhere in 2018. Detection of the wave and the roughness of the sea. What sort of scale range does that increase? Unfortunately, I can't. I would need to look it up. I don't have any experience with working with SAR on sea.
Okay.
So
no worries. Thank you.
should we just wrap it up then?